Okay. So, let us continue the discussion of the compressible flow. This is just we started off, and what we are trying to discuss now, how this sound wave is generated and how one can estimate the speed of sound. So, this is what we talked about, that the speed of sound and the transmission process. So, the process is supposed to be an isentropic. Now, since this process is isentropic, what one can write, that P by rho to the power gamma is constant, let us say C. So, this is P rho to the power minus gamma is C. Now, if we take an differentiation of this, so this would be minus gamma plus 1 P plus 1 by rho to the power gamma dP by d rho, which is 0. So, taking the different or differentiating this expression with respect to density. So, what I get, 1 by rho to the power gamma del P by del rho at S equals to gamma by rho to the power gamma plus 1, which is gamma rho by P. So, what we get from here is that del P by del rho, which we get for isentropic process, is gamma P by rho. Again, for perfect gas, what we can write is P equals to rho R T. So, that means P by rho is R T. So, what we will write, that del P by del rho for isentropic is gamma R T. Okay. So, what was the speed of sound? This is del P by del rho S, which is root over gamma R T. Now, this is how you can estimate the local speed of sound. Now, when you talk about the speed of sound or you estimate the speed of sound, immediately there is another important thing which comes in place, is that the Mach number. So, the Mach number is ratio between local speed to the speed of sound. And why this number is important? Because this can categorize the flow field in different zones, like for example, it could be less than 1, it could be 1, it could be greater than 1. So, when it is less than 1, typically we call it subsonic flow, 1 is sonic flow, when it is greater than 1 it is supersonic flow, like this. But now, when it goes beyond Mach 5, then we call it as a hypersonic flow also. So, that is what it happens in your scramjet application, or the intake is. Now, typically m less than 0.3, where in this range the density variation is pretty much negligible, and that is why this is where the it assumed to be a incompressible zone or incompressible flows, incompressible flows, because the variation in density is quite small or rather negligible. Again, mind it, we are not talking about incompressible fluid, this is incompressible flows, because this is a very common mistake that one can do. Still, the even if it is air, fluid is compressible by nature, but it is in that limit this is becoming the flow is happens to be the incompressible. And as I said, it could be another could be Mach greater than 5, which is hypersonic flow. Okay. Now, one may think about what the physical interpretation of this Mach number. Mach number, one can think this is a ratio of two energy, one is kinetic energy, the other is internal energy. So, how you do that? I mean, just a simple way to look at that. I mean, let us say kinetic energy by internal energy. So, we write CBT, which is V square by 2 RT gamma minus 1, which would be gamma B square by 2 divided by A square by gamma minus 1. So, this would be gamma by gamma minus 1 by 2 Mach number square. So, that is what it happens, what I said, this is a ratio between kinetic energy and internal energy. So, with that we will start the 1D compressible flow. Now, let us consider a region here like this. Okay. We draw a control volume. Okay. And this sides there are flows coming in, this side this goes out. This is one dimensional. So, let us define the coordinate system, and this could be the area. So, at the inlet all properties are like P1, T1, rho 1, U1, and here P2, U2, T2, rho 2, E2. So, what we are considering here, the flow of a gas through this 1D region. So, this region could be normal shock wave or region with heat addition. Now, the properties of flow changes as it flow across this region. So, let us consider this control volume here, which we have drawn, and they are between station 1 and 2, and A is the area of the control volume, which is perpendicular to the flow. Then we can have some more assumption like steady flow, no body forces, no potential energy, implicit flow. So, these are the assumption that you can have. Then what you can write, you write down the conservation equation of mass or the continuity equation. So, first thing that you write the continuity equation. So, if I write the complete continuity equation which we have derived, now that is how it looks like, which is 0. Now, there are assumption of steady flow. So, this goes to 0 because of steady flow. So, what it gives us back is the control surface V dot n, which is 0. Now, so we will write this one at station 1 rho V dot n dA plus as station 2 rho V dot n dA, which is 0. Now, if we go about those drawn control volume, so this will become rho 1 u 1 a 1 plus rho 2 u 2 a 2. Now, the area is same, constant area. So, this becomes rho 1 u 1 equals to rho 2 u 2. That is, let us say, equation 1. So, this is an continuity equation for steady 1D uniform flow. This is for steady 1D uniform flow. That is the continuity equation. Similarly, we derive the momentum equation. So, first we can write the complete form, which is control volume rho v dV rho v b dot n dA summation of SS plus B. Now, again this goes 0 because of steady, this goes to 0 because of no body force. So, we get this equals to sum of that. Now, this could be the sum of the surface forces. So, similarly, we will write rho 1 minus u 1 a 1 u 1 plus rho 2 u 2 a 2 u 2 p 1 a minus p 2 a. So, let us replace this a 1 as a and a 2 as a. So, they become consistent. So, what we get p 1 plus rho 1 u 1 square p 2 so that is equation 2. This is an equation or the momentum equation for steady 1D flow. Okay. So, you see, when we write down the complete equation system and then simplify with the assumption, this makes things much simpler. So, similarly, you could write the energy equation rho V dot N dA. Now, no shaft torque, this goes to 0, this goes to 0 for steady, this goes to 0 for no body force. So, this becomes q dot equals to h 1 plus v 1 square or u 1 square by 2 minus m dot 1 h 2 plus u 2 square by 2 m dot 2. Now, from continuity equation we know m dot 1 would be m dot 2, or let us say it is m dot, then you get q dot by m plus u 1 square by 2 h 2 plus u 2 square by 2. Now, this if we write, then I can write that. So, h 2 plus u 2 square by 2 is h 1 plus u 1 square by 2 plus q, where q is the heat added per unit mass. So, that is equation number 3. This is for energy equation steady one dimensional flow. Now, this is one way to look at the energy equation, but there could be an alternative way, and which could be quite handy, because when we deal with compressible flow, maybe the alternative form would become handy. Let us look at that. What is that alternative form of energy equation? So, let us consider the same one dimensional flow, what it is there, and then assuming adiabatic flow, which is no heat addition. So, what we get, that h 2 plus u 2 square equals to h 1 plus u 1 square by 2, because there is no heat addition. Considering the perfect gas, which is H equals to Cpt, where Cp is constant, then what I can write, that Cp T1 plus u1 square by 2 equals to Cp T2 plus u2 square by 2. So, that is, let us say, equation number 4. So, alternatively one can write gamma r by gamma minus 1 T1 u1 square by 2, gamma r by gamma minus 1 T2 plus u2 square by 2, which is equation number 5. So, this one is u1 square plus u1 square by 2, which will become a2 square by gamma minus 1 plus u2 square by 2. So, that is an alternative way one can write this energy equation. So, let us have some other definitions in place. where we consider a point, let us say A in a flow field. Now, at A, fluid element is travelling at some velocity and speed. So, that is m v, static pressure is P and temperature is T. So, at the point A, which we have considered is inside the flow field, the fluid element is travelling at some Mach number and velocity, pressure and temperature. Let us imagine the fluid element is adiabatically slowed down. So, the fluid element is adiabatically slowed down, or that is if Mach number at that point A, if the Mach number is greater than 1, then it is slowed down, or speeded up if Mach number is less than 1. So, this is done until m A is 1. So, that means to reach a sonic speed at A, if the upstream fluid is at higher speed, then it has to be slowed down, but it is done adiabatically. If the upstream fluid is at the lower speed or the subsonic, then it has to be speeded up to reach that sonic speed. Now, what happens as m changes adiabatically, the fluid temperature also changes. So, when the fluid element arrives at m equals to 1 from its initial state at m and t, let us say the new temperature is T star. And let us say the speed of sound at this hypothetical condition, which is m equals to 1 as A star, and which can be find out that gamma r T star. Now, one can note here for any flow with Mach number m and temperature T, we can associate it values of so T star and A star. So, let us consider again the same fluid element at A. Now, consider again the same fluid element at A. Now, imagine that we isentropically slow this fluid element to 0 velocity. That means stagnate the flow. So, which indirectly means isentropically the fluid element has been brought to 0 velocity. Now, the pressure and temperature of the fluid element when V is 0 are defined as stagnation pressure and stagnation temperature, which is naught. That means at the velocity 0 condition, this is what the pressure and temperature would be. These are called the stagnation pressure or stagnation temperature. Now, actual pressure P and T, these are called now static pressure and temperature. Now, for static flow or no flow, for no flow, P naught would be P and T naught would be T. So, the characteristics Mach number, Mach number, which is m star, is V by A star, whether the real m is V by A. Similarly, stagnation speed of sound, which would be A naught, that is gamma r T naught 0, and stagnation density, which is rho naught equals to P naught by R T 0. Now, considering equation 5, what we can write now, A 1 square by gamma minus 1 plus U 1 square by 2, A 2 square by gamma minus 1 plus U 2 square by 2. Here point 1 corresponds to point A and point 2 corresponds to the imagine condition, where the fluid element is brought to m equals to 1 adiabatically. Okay. So, actual speed of sound at point A is A, actual speed of sound at actual velocity at point A is u. So, what we can write, A square plus gamma minus 1 plus u square by 2 A star minus 1 u star by 2. So, this will give us A square gamma plus 1 by 2 gamma minus 1 A star square. So, this is what is equation number 6 that we get. So, for two different points, we get this relationship between speed of sound and the A star. So, we will stop the discussion here and continue from here in the next session.